In this video, we're going to go over polar equations and their graphs. So I recommend you save this first chart here, a piece of information, take a screenshot or what have you, because it's a good reference for all of the different types of polar equations and graphs. Now, if you have a polar equation for a line that makes an angle theta with the polar axis, with our positive x-axis, rectangular, that equation would be written as y equals mx, but we know we can get the slope m by taking tangent of that angle alpha. And the polar equation would just be theta equals alpha. That would make a line, because remember, theta represents the angle from the positive x-axis. And so you would just have any radius, that's why it's a line that extends forever, as long as that angle was consistent. Okay, the equation for a vertical line, since we know x is equal to r cosine theta in polar, we would have r cosine theta equals a, that would be a vertical line, and horizontal, r sine theta equals b. Okay, now onto circles. Polar is especially useful when you're graphing circles because we know the rectangular equation is x squared plus y squared equals a squared. But in polar, all you need to do to graph a circle is write the equation r equals a. And that would represent a circle that's centered at the origin, whose radius is a. Notice there's no theta in the equation, which means theta can take on any value here. Okay. Now, the next two are very helpful, especially when you move on to calculus 3. If you have a circle whose center lies on the x-axis, you're going to have either plus or minus 2 times a. A is the radius cosine theta. So cosine theta is your big clue that it's centered on the x-axis. And then whatever constant is in front, that's the diameter. So it's twice the radius. Similarly, if you have r equals plus or minus 2a sine theta, the sine theta is your clue that your circle is centered on the y-axis. And again, the radius is a. Okay? All right, other equations that we graph in polar. So we have a cardioid, and it's called that because it looks kind of like a smashed heart. Do you see it? It looks kind of like a cardioid. It'll either open up on the x-axis or be centered along the y-axis, depending on if you have a sine theta or a cosine theta. The big way to know that you have a cardioid is that the constant here and then the constant in front of cosine or sine are equal to each other. It just might be positive or negative. Now the next two are called limaçon. That's C, that's the French C, okay? So you have one of those when the constant being added to the trig function is different than the coefficient of the trig function, okay? And it has no inner loop, so it basically looks like a cardioid when this constant here is larger than b, than the constant in front of the trig function. There's this cute little inner loop here when this constant a is less than b, okay? So just keep those straight. It's helpful if you know what the graph should turn out to be looking like before you start trying to make your graph, because it'll just give you a good guide. Okay, next one, pretty cool, is the lemniscate. And it looks like an infinity sign. And you know you have one anytime you have r squared equals, and it's either a squared cosine 2 theta or a squared sine 2 theta. All right? And then you can have roses, not just 3 petals, 4 petals. You could have 5, 6, etc. But here's how you know how many petals there are. It could be for sine or cosine. If you have an odd coefficient on theta, then that's the number of petals you have. So if it's 3 theta, 3 petals, 5 theta, 5 petals, 7 theta, 7 petals. If it's an even constant in front of theta, you have double that number of petals. So basically, if you had, let's say 2 theta, that's why there's 4 petals. If you had 4 theta, there would be 8 petals. If you had 8 theta, there would be, you got it, 16 petals, okay? So anyways, that's that. And we're gonna look at some examples here. So identify and graph each polar equation. The first one is r equals 1 plus sine theta. So let's first identify it. This is gonna be a cardioid. How do I know that? Well, The constant here, a, is equal to the coefficient on sine theta, so they're both 1. And usually you just start off by making a table of values, old-fashioned way. So theta and then r equals 1 plus sine theta. So you're going to substitute in values for theta into the function and then plot them from there. Now, one thing you can do that's going to make it a little helpful is you could always graph y equals 1 plus sine theta and use the graph to help you get values for the table, right? So we spent a whole bunch of time graphing trig functions. Let's use that to our advantage. So remember, sine's period is 2 pi, and then this has been shifted vertically up 1 unit. So here's 1, here's 2. So I'm going to have pi over 2, pi, 3 pi over 2, and 2 pi. And the graph, sine's graph starts in the middle. Oop, no, it'll start at 1, sorry. And then it's going to go up to 2 at pi over 2, back to 1, down to 0, back to 1. So this is the graph, just one period. And one period will trace out the complete graph of the cardioid, because if you keep repeating, you're just going to get the same points again. Okay. So let's get the points from here for our graph. Like this is pi over 4, right? This is 3 pi over 4. This is 5 pi over 4. 7 pi over 4. Okay. And when you're first getting started, it's helpful to plug in quite a few values. So I would start at 0, and then here, this is 0, so the value would be 1, or you could just plug in 0 for theta. Pi over 6, okay, pi over 6 would be about here. And then I would know, okay, well that's 1 plus sine of pi over 6 is a half, so this is 1.5, or you could just read it off the graph. Pi over 4, that's going to be 1 plus rad 2 over 2. Okay, if you haven't memorized this yet, it will be very helpful. Rad 2 is approximately 1.4, and rad 3 is approximately 1.7. Okay, both of those come up so much in your math career, it's just worth memorizing. Okay, so if I'm plugging in pi over 4, right, rad 2 over 2, that's going to be 1.4 divided by 2. So that's 0.7 plus 1, so this is about 1.7. Honestly, if you just go to the 10th place, that's good enough. Pi over 3, that's going to be 1 plus rad 3 over 2, so that's about 1.9. And then pi over 2, you can see clearly from the graph at pi over 2, it's 2. And then we have 3 pi over 4. So 3 pi over 4, now that's going to match what I had at pi over 4. Can you see that? Here's pi over 4, here's 3 pi over 4. These values are going to be the same. So this is going to be 1.7. And then at pi, I have 1. Okay, 5 pi over 4, that's going to be 0.3, right, over here. So 5 pi over 4, that's going to be 1 minus rad 2 over 2, or 1 minus 0.7, so that's about 0.3. 3 pi over 2, we have 0. You can see that there. 7 pi over 4, we have 0.3, and then 2 pi, we're back at 1, okay? Notice in the beginning, I put a lot more values in, like for the first quadrant, I did pi over 6, pi over 4, pi over 3, and pi over 2, just to kind of help me get a feel for what's going on. And then after that, I kind of skipped, and you can do that too, and then fill in gaps if you're not comfortable with what the graph's gonna look like. Okay, so let's start filling things in. So we have, when theta is 0, r is 1, so that would be right here. When theta is pi over 6, r is 1.5, so maybe about there. When theta is pi over 4, we have 1.7. At pi over 3, 1.9. And then at pi over 2, it's all the way up here at 2. And then 3 pi over 4, this is 3 pi over 4 right here. We're at 1.7. So 1.7 at pi, we're at 1. And then we have 5 pi over 4. Here's 5 pi over 4. We're at 0.3. 3 pi over 2, 0. 7 pi over 4.3, and then 2 pi 1. So if you want, you could mirror. So I could mirror this point, excuse me, and this point here, because I know it's going to be symmetric. I just didn't substitute all those values in the table, but if I want a more complete graph, I could add those in. And then here's our cardioid. You see the little dimple? It looks like a heart, sort of, upside down. And it's centered on the y-axis, which makes sense because there's a sine theta in here. Okay? Good. Let's look at another example. We have here 2 minus cosine theta. Okay, so what is that going to be? Well, it's a limaçon. Without the inner loop. That's because A is larger than B. Okay? So you could draw the graph of 2 minus cosine theta if you like, or I'll just show you how to make a table and go from there if you don't feel like making the graph. So we have theta and R. And I'm going to start off by putting almost all the values, that we know from the unit circle in the first quadrant. So 0, pi over 6, let's do pi over 4, pi over 3, pi over 2, and then from there maybe we'll just do 3 pi over 4 and pi and see what happens. Okay? So at 0, we're going to have 2 minus cosine of 0, which is going to be 1. So 2 minus 1, that's 1. So 0 is 1. At pi over 6, I'm going to have 2 minus rad 3 over 2. So rad 3 is about 1.7. If I divide it by 2, it's 0.85. So 2 minus 0.85 is going to be 1.15, so let's just say about 1.2. All right, good, let's keep going. So at pi over 4, cosine's rad 2 over 2, so about 0.7, so 2 minus 0.7, that's about 1.3. Pi over 3, cosine's a half, so 2 minus a half is 1.5, 1.5. Pi over 2, cosine is 0, so this is going to be 2. At 3 pi over 4, cosine is now negative 0.7 approximately. So then that's going to be 2 plus 0.7, so 2.7. And then at pi, cosine is negative 1. So 2 minus negative 1, that's going to be 3. Okay, let's graph what we have so far. So we have 0, 1, pi over 6, 1.2, pi over 4, 1.3, pi over 3, 1.5, pi over 2, 2. Oh, that 1.5 was too aggressive. Hold on. This is 1.5. Now it's at 2. Okay. Then at 3 pi over 4, we're at 2.7. All the way over here. And then at pi, we're at 3. 1, 2, 3. Okay, good. From here, if you want to just fill in, it looks like it's going to be centered on the x-axis, right? Which doesn't surprise us because of the cosine theta. We can just do 5 pi over 4. And I know that's going to be the same as at 3 pi over 4. We're going to have 2.7. So 2.7 maybe about here. And then we could do 3 pi over 2 and cosine 0 there. So this would be 2 again. So that would come right here. And then if I want to do another value, maybe 7 pi over 4, then that would give me the same value as at 1.4, which is, or pi over 4, which would be 1.3. So somewhere around here. Okay, and then again, like before, if you want to reflect a few here, over on the other side, you can do that. So remember that first one was 1.2. That's 1.3, and then 1.5. So if you want to have a nice little mirror image, you can. I'm going to actually outline it in a different color so you can still see all the points. Okay. Good. How are you feeling? These are tedious, but they can be fun. Okay, let's spice things up. We're going to do another limaçon, but this time it has an inner loop. How do I know that? Well, because A is less than B. So this is a limaçon with an inner loop. Okay, so here we go. Let's make our table. Now I'm doing my best to pronounce this according to the French pronunciation because it's a French word, but excuse me, I haven't taken French in several years. And maybe if your teacher doesn't even bother, they'll say something like Limacon, which, anyways. So we have theta, and then r equals 1 minus 2 sine theta. Let's just start filling in the same way we did before. So we have 0, pi over 6, pi over 4, pi over 3, pi over 2. I usually like to fill in a lot in that first quadrant, and then I start jumping. Then I'll do 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and then if you start getting nervous and you want more points, you can add to it. Okay, so let's see here. So sine of 0 is 0, so 1 minus 0 is 1. Sine of pi over 6 is a half, so 2 times a half is 1. 1 minus 1 is 0. Pi over 4, I'm going to have 1 minus 2 times rad 2 over 2, so it's just 1 minus rad 2. And remember, rad 2 is about 1.4, so 1 minus 1.4 is about negative 0.4. Pi over 3, I'm going to have 1 minus rad 3, so negative 0.7. And then at pi over 2, sine is 1, so 1 minus 2 is negative 1. And then the values are going to repeat on the other side, right? 3 pi over 4, sine has the same value, so this is going to be negative 0.4. And then at pi, sine is 0, so 1 minus 0 is 1. Now at 5 pi over 4, sine is going to be negative rad 2 over 2. If I multiply that by 2, then that's just negative rad 2, so this is going to be 1 plus rad 2, or 1 plus 1.4, so 2.4. And then similarly, 3 pi over 2, sine is negative 1. So negative 2 times negative 1 is positive 2, plus 1 is 3. And at 7 pi over 6, 7 pi over 4, sine is going to be, again, negative rad 2 over 2, but then it's going to get multiplied by a negative 2. So I'm going to have 2.4. Okay, let's plot this. 0, we have 1. Pi over 6 is 0. Ooh, how strange. Okay. Pi over 4 is negative 0.4. So remember, here's pi over 4, but when it's a negative radius, you go in the opposite direction. So here's pi over 4, but I have to go in the opposite direction, 0.4, since the radius was negative. So maybe here. I'll zoom. Is that helpful? And then pi over 3, also we have negative 0.7. So pi over 3, he's right here. And we have negative 0.7. So maybe about here. And then at pi over 2, negative 1. And then 3 pi over 4 is negative 0.4. So here's 3 pi over 4, but we got to go negative on that one. 0.4. That's maybe a little too far. Let's go closer. Okay. And then at pi, it's 1 over here. Whoa, did you see that happening? And then 5 pi over 4 is 2.4. So this is 5 pi over 4. It's going to be 2.4. So maybe to here. At 3 pi over 2, we're at 3. At 7 pi over 4, we're also at 2.4. Okay, do you kind of see what's going on? I feel like we need another point just to complete the picture. Let's add 7 pi over 6 here. Why am I doing that? Because I want that inner loop nice and complete. So 7 pi over 6, here's 7 pi over 6, right? So sine at 7 pi over 6 is going to be -1/2 times -2 is going to be +1. 1 plus 1 is 2. So it's 7 pi over 6, it's 2. And then I can reflect that over here. It would be the same thing for 11 pi over 6. And then you can also reflect over points from that inner loop. Okay? Good. So this is how it's all going to look. Again, I'll fill in the graph with a different color so you can see all the points. So you've got the inner loop here. That's the little inner loop. And then this part comes up and around, almost like a cardioid or just a regular limaçon without sans the inner loop. See it? Okay. So those can be a little bit tricky, and feel free, like I did, if you need to add more values for theta to your table, that's fine. Okay. Good. Last one. Let's end with something fun. So we have r equals 2 sine 3 theta. I say these are fun because I love drawing roses. So this is a rose with 3 petals. How do I know there's 3 petals? Because there's a 3 in front of the theta. Okay. Now, anytime this happens, in order to draw the graph, you're going to need to add values for theta in your table that you don't typically use. Because remember, if you remember back in the day from graphing, we would, when you have a coefficient in front of the angle, that changes the period, right? And you would actually divide the period by 3 in this case. So your period is 2 pi over 3, meaning the graph is going to repeat more often, and I'm going to have to plug in smaller values of theta than normal to get the complete graph. So normally, maybe you would just start with pi over 6. So in that case, I'm going to divide that by 3 and plug in pi over 18. You see? And then instead of plugging in pi over 4 next, I would divide that by 3 and plug in pi over 12. And then instead of plugging in pi over 3, if I divide that by 3, then I would plug in pi over 9. You get the idea? Okay, so do that until you feel comfortable. So we have pi over 18, pi over 12, pi over 9. Then I'll add to that pi over 6, pi over 4, pi over 3, pi over 2, and then let's see what things look like at that point, and then we can decide how we want to build the rest of our table. Okay, good. So let's see. So pi over 18, like I mentioned before, so you're going to take that angle, pi over 18, multiply it by 3. I'll write this first one out for you, but you really should do them in your head. So you have 2 times sine, 3 times pi over 18. So that's 2 times sine of pi over 6. Well, sine of pi over 6 is 1/2. So it's 2 times 1/2, which is 1. Okay. Now pi over 18, that's not marked off here for us. So remember this one here is pi over 6. So just cut it in thirds. So maybe a third of the way here or so. Okay. That's a third of the way. And the radius is 1 there. Okay. Pi over 12, you're going to do the same thing. So that's going to be 2 times sine of 3 times pi over 12, which is going to be pi over 4. So that's going to be 2 times rad 2 over 2, which is rad 2, which we now know is about 1.4. So pi over 12, maybe that's like halfway here, right? Halfway up to pi over 6, and it's going to be 1.4, somewhere around there. Okay. Pi over 9. So if I plug in pi over 9, that's 2 times sine of 3 times pi over 9 is pi over 3. And then sine of pi over 3 is rad 3 over 2. But then times 2 is rad 3. So this is about 1.7. So pi over 9, that's going to be 1 pi over 18, 2 pi over 18. So 2/3 of the way. So here's pi over 9. let's say 1.7's around here. Okay, all these dashed lines are getting messy, so I'm erasing them because I want to be able to focus on the points here. Okay, good. Now the rest I'm just going to do the math in my head. So pi over 6, first you multiply that angle by 3, so it's going to be pi over 2, and then sine of pi over 2 is 1, so 2 times 1 is 2. Pi over 4, you're going to have 2 times sine of 3 pi over 4, right? So that's going to be rad 2, so about 1.4. Let's add those in now. So pi over 6 is 2, and then pi over 4 is 1.4. And then pi over 3, that's going to be 2 times sine of pi. Well, sine of pi is 0. So at pi over 3, it is 0. So we've closed one loop. You see, we started there and went loop-de-loop. And at its max, the rows had length 2, right? Because of that coefficient there. Okay, let's keep going. So at pi over 2, I'm going to have 2 times sine of 3 pi over 2, which is -1. So this is -2. So at pi over 2, you're going to come over here and plot -2. And I know that's going to be like where the other petal extends. That's going to be the end of the other petal. Okay, I'm going to keep going. So we need maybe 3 pi over 4. Maybe I'll throw in a 5 pi over 6, 11 pi over 12, and then let's see what happens. Okay, so 3 pi over 4, that's going to be 2 times sine of 9 pi over 4. So that's the same as sine of pi over 4, and then times 2 is just rad 2, so that's about 1.4. So 3 pi over 4, we have 1.4. And then 5 pi over 6, this is going to be 2 times sine. 5 pi over 6 times 3 is 5 pi over 2, which is the same as pi over 2, so this is 2. So 5 pi over 6, now the radius is all the way here at 2, and then I know now where that third petal is, right? So whenever the radius comes out to be 2, which is the coefficient here, you know that that's the tip of, or the end of the petal. And since I know there's 3 petals, I know where they all are. So I can just fill in the rest of my graph now. And if you want to, you know what, let me mirror the points that we had here. Like if I want to reflect this one over here a little bit, I can do that. So I have a nice shape. So it's going to come through like this. There's the second petal. And then the third petal is going to be down here. If you want to plot more points on your table, feel free. But otherwise, I feel comfortable that we know what it's going to look like. Okay? Let's zoom in and really make it look pretty. Okay. And another way that you could gather the points or know where the tips of the petals are going to be is if you were to graph the function. If you were to graph 2 sine 3 theta, then it might be helpful when you're making your table to know once you've completed enough petals and where it's going to repeat. So if you wanted to do that, okay, if you're going to graph y equals 2 sine 3 theta, the period would be 2 pi over 3. And so the step is the period divided by 4. So 2 pi over 3 times a fourth is going to be pi over 6. And so I could graph this if I wanted. Amplitude is 2. And here's theta. And the step is pi over 6. So I'll have 1 pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, which is pi over 2, 4 pi over 6, which is 2 pi over 3. And that's the period. And this is sine. So it would start here, go up, back to pi over 3, down, and back here. And then you could gather more points this way. So you could break up this interval here. Here's pi over 18, pi over 9, and you can keep going and get the values from the graph as well, okay? The graph kind of just helps you know when the loop's closing, when you have symmetry, right? When the y values are the same, since we're dealing with sine. All right, good. We never even, did we plug in 11 pi over 12? No, let's do it. I feel bad that it's there and we didn't do it. So this is going to be 2 times sine of 11 pi over 4. So that's the same as 3 pi over 4. So that's going to be rad 2. So about 1.4 at 11 pi over 12. Oh, that's this guy that we reflected earlier. Okay, so that concludes the lesson on graphing polar. Make sure you just take your time and feel free to keep adding as many points to the table as you need to get a good graph.